Welcome back. Did I tell you that I'm going to leave the rest of this review to students? Well, I did, but let me change my mind. Let's go over to several problems here to help you reviewing these things. We just went through one example and it was this one. That was pretty much standard. You simply take y as the inside of the composite function and then follow the procedure, and then the problem just takes care of itself by repeated simplification. The same, y is inside, same whatever other character, u is the denominator, which is inside of the reciprocal function, inside of the radical, inside of -1/2 power function. And this one is a little bit less visible, but if you express tangent as sine of a cosine like this, then you can clearly see that the denominator is the inside, so it'll work out. In short, in these kind of problems, you didn't really have to worry too much about the second criterion here. Number one, is there a composite function? Simply take y as an inside, and usually that was enough. But in some cases, that's not enough, and you have to consider second criterion, and that's why I'm taking a little bit of extra time reviewing this again. Let's move on to this set. And let's go over to this problem. It is tempting to take my substitution as entire denominator, kind of like this. U as x log of x. And then what is my du? Du is, we'll have to take the derivative of x log of x, and at this moment you should see that this is not really working out. But let's suppose that you didn't see it. So take the derivative using product rule, 1 times log of x plus x times the derivative, 1 over x du dx, excuse me, will be my answer. So if you solve for dx, then dx will be du over something like this complicated in denominator. Wait a minute, this is not really working out. The purpose of substitution is to make the integral simpler than before. Basically, it's a simplification. But I'm achieving the opposite here. I'm making it worse. It's not working out. So we'll have to take some other substitution or use something else. How do we do that? That's where the second criterion works. Is there the derivative or candidate of the derivative flying around? Here, if I take my substitution as log of y, let me show you, then the derivative of this log function is 1 over x. And that is visible right here, 1 over x. Do you see it in the integrand? You should. That's correspond to the second criterion here, and that gives you that's an indication that y equals log of x is correct substitution. Okay, let's go ahead with this correct substitution then. Y is log of x, derivative, and then dx is x dy. And then this log of x, let me highlight in red, is substituted by y here. And this dx, let me highlight it, is substituted to x dy. Do you see a simplification? Yes, you should. This x and that x cancel each other out. You just have a y integral. Calculating this y integral, you're going to get log of y. Substituting log of x back in, you have the answer. So once you see a correct substitution, everything is easy from that point on. Let's do this one more time, and let's move on to problem C here. I like this problem because Calc 2 is much heavier in trig than Calc 1. And this one is about trigonometric functions. As a matter of fact, this one is about 2 trigonometric functions, sine and cosine. And as a matter of fact, there's going to be another one showing up later on. So how do you work out? It is tempting to take y as the entire denominator, 1 plus sine squared at theta, and take the derivative. At this time you'll see derivative of 1 plus sine squared, it's too complicated. you're going to end up making it worse than before. So that's not the right way. So let's go back to this criterion, blue one. And is there a derivative of inside or a candidate of the derivative flying around? Let's go back to the integral. This cosine of theta is a derivative of a sine function. Do you see that? That corresponds to this blue criterion, the second one. So if I take my substitution as sine of theta, as I do it here, this time let's use character s. S is sine of theta, then the derivative ds d theta is cosine of theta, so the theta is 1 over cosine of theta times ds, as we have in the first line, and let's substitute everything back in. The sine squared will become s squared, which I highlighted in red over here, and this d theta will be substituted to 1 over cosine of theta times ds, which is highlighted in blue here. Do you see a cancellation? Yeah, cosine of theta cancel each other out, and we have just s integral 1 over 1 plus s squared. And what is that antiderivative? It's an arctangent. So arctangent of s is correct antiderivative, but it is expressed in terms of s, not in terms of theta. So let's take the final substitution, s as sine of theta, and plug it back in, and then arctangent of sine of theta, and there goes the answer here. So second criterion, the blue one, is important here. This one. Oh, by the way, this blue and those blue are not the same. They're not related, as a matter of fact. Happen to be just two different color codings. Okay, let's go move on to another exceptional or non-standard substitution. And let's move on to, say, this problem. First step is easy. If you simply take y as the inside of this radical, that's pretty obvious, isn't it? We have negative 1/2 power function. What's the derivative? Derivative is 2x. Do you see x here? I don't see x, but I see x cubed. That's going to be a bit of a problem, as you see over here. Take y as 1 plus x squared. Take the derivative. dy dx is 2x. Solving for dx, we have dx equals 1 over 2x times dy. Great. And plug everything back in. 1 plus x squared will turn out to be the same as y. That's my substitution number 2. And this dx is the same as 1 over 2x times dy. That's the computation we did. And we have this substitution number 2, and after cancellation, this is what we got. Here's a problem. This is not entirely a y integral. We have still x squared, and somehow we have to do something further to this x squared. Otherwise, we cannot calculate this integral. I've seen some students getting this x squared outside here. That's not right, because x and y are related. How are they related is the key question here, and the answer lies right here, the red one. The relation between y and x is y equals 1 plus x squared, and you can use that to find out what x squared is. What is it? Here we go. This x squared is same as y minus 1. So here we are. We have a y integral. How do you calculate this y integral? Well, this is a review for what we did in Calculus 1. If you have addition or subtraction in the denominator, that's going to be a problem. You'll have to use substitution or some other technique. But if you have addition or subtraction in the numerator, no problem there. You can simply distribute and separate the numerator. This is what I did. Instead of y, square root of y in the denominator, express this as y to negative 1/2 power, and then distribute, and I have a bunch of power functions added together. Applying the power rule, one term at a time, we have this answer, and substitute for the third time now, y equals 1 plus x squared, here and there, and we have the final answer. This was kind of extensive problem. Substitution, and then residual x term. Substitution again, extra substitution. And then how to take care of this is related to how to take care of denominator, which is monomial or just single power function. Okay, that was a fun example, and let's move on to final topic of this review, how to deal with a definite integral. Let's go with this example. We have done this before, as a matter of fact. Cosine of theta over 1 plus sine squared. We had an arctangent function, didn't we? How do we take care of this kind of integral? There are two ways to handle a definite integral. Solution 1, which works well in calculus 1 and works okay most of the time in calc 2, is completely finishing the antiderivative computation and plugging in theta equals pi over 2 and theta equal to 0 and subtracting one from the other. Kind of like this. We have done this before. Substitution, workout, second substitution, simplification, we have a y integral, integral computation, third substitution, and here we are, we have the final answer. Alright, final answer to antiderivative, excuse me. Not the final answer to this problem. So, okay, let's calculate the definite integral. So here's the antiderivative, indefinite integral, and plug in theta equals pi over 2 and theta equal to 0, subtract one from the other, that's the fundamental theorem, and calculate out, we end up with pi over 4. This works well, but not always. There are some examples that this method will break out in Calc 2. Even in Calc 1, there were some examples, especially when you have absolute values. It's just that instructors do not usually go over those kind of problems in Calc 1 level. Here, we are forced to do that because we have strict substitution. But more importantly, if you go over to Calc 3, this method will completely break down. So in Calc 2, I'm going to emphasize the second solution more. Here we go. After initial substitution and the derivative computation, we take an extra step right here. When theta is equal to 0, as you see over here, and plug in theta equal to 0, and we have y equals sine of 0, so y is 0. Plug in theta equal to pi over 2, right over here, that's the end point, and y is sine of pi over 2, so y is equal to 1. What does it tell me? As theta is moving from 0 to pi over 2, y is moving from 0 to 1. So after this second substitution and getting a y integral here, I can plug in y equals to 1 and y equal to 0 directly here and subtract one from the other. So the third substitution was unnecessary. By fundamental theorem, we have pi over 4 minus 0 like this, and we have the same answer. So here's a trade-off. A little bit simpler integral computation down here, and the trade-off is one extra step here. So in terms of integral computation, it's about the same as solution number 1. So I prefer this method, and even when I teach Calculus 1, I do emphasize this method a little bit more. However, I tolerate students doing solution 1, just completing the antiderivative and plugging in at the very end, because it works out okay in Calculus 1. In Calc 2, it still works out okay most of the time, so I'm not going to take off any points for using solution 1, but I'd like to emphasize solution 2 far more, because number 1, there are some examples in Calc 2 that solution 1 fails. Trig substitution is a good example. And number 2, we have to prepare for Calculus 3, multivariable calculus, Math 2730, and that's where the solution 1 will completely break down. So let's move on to, let's emphasize solution 2. Here are other problems. Oh, I didn't put any of those answer keys here. No, just the answer, but no derivation. I emphasize using solution 2 more than solution 1. Are there some other problems here? Some area computation problems related to substitution type integral. Okay, here's a good exercise, you can do that. Another good exercise you can do with area computation with substitution. Good.